Good morning everyone, my name is Jérôme Gâteau and I'm a CNRS researcher at the Laboratoire d'Imagerie Biomédicale. I'm going to talk to you today about photoacoustic imaging. I will give the talk in English, but feel free to ask your question either in English or in French at the end of the talk. So today I will talk about mapping optical absorption from cellular scale to preclinical imaging with photoacoustic imaging. As this modality is maybe not familiar for you, I will give the basic concept of the photoacoustic principle and the overview of the imaging capabilities. So first, what is photoacoustic imaging? And already we can see that I highlighted the two different parts, so photo and acoustic. So from that we can already see that it's a multi-wave modality with light and sound. And the optical, here the optics is for the optical excitation, and we have ultrasound detection. So photo for the optical excitation, acoustic for the ultrasound detection. And in between, there's the biological tissue that we want to image and the photoacoustic effect. So the optical excitation, it brings an optical absorption contrast, and optical absorption in the body can be endogenous, like hemoglobin, lipids, DNA, RNA, or exogenous, like dyes or nanoparticles. The ultrasound detection brings properties about imaging depth that is increased compared to all optical imaging, and spatial resolution. And the ultrasound resolution is indeed submillimetric at centimeter depth. So how does it work, this optical generation of ultrasound? So the first components are optical excitation, ultrasound detection, and the third one is optical absorption. And for the optical excitation, we are using a nanosecond pulse laser, which is the most common optical source for photoacoustic imaging. And for the ultrasound detection, we can use detectors that are used in ultrasound imaging, like a piezoelectric single element detector or an array of detectors. So here it's a line of 128 elements, detectors arranged so in this direction. And what's gonna happen is that we shine light on the optical absorbers. Some optical energy is absorbed from this incident light. Temperature increase, pressure increase due to the thermoelastic expansion, and from that ultrasound wave are going to propagate to the ultrasound detector and are recorded as radio frequency signals over time. And from those signals we can get the photoacoustic image. So a bit more about the physical principle. So what we record is the pressure field over time at the detector, but the initial pressure rise coming from the optical absorption is here, and it can be written with this formula, where so the pressure rise is proportional, is equal to the product of all those terms, and we can group them into two parts, where these three terms corresponds to the absorbed optical energy converted into heat. So the absorbed energy, it's the local absorption coefficient time the optical fluence, and we have a photothermal conversion efficiency to get the portion of the optical absorbed energy that is actually converted into heat. And to convert the heat into pressure, there's a conversion coefficient here called the Gunn-Eisen coefficient. Then from the initial rise, there's the propagation to the detector, and you can recognize here the initial pressure rise, and there's this term which corresponds to spherical wavelet. So each point just radiate ultrasounds as a point source, a spherical point source, with this time profile corresponding to the time duration of Dirac function. And because the biological tissue are mostly weakly scattering to ultrasound wave, we can assume that we propagate in free space. The inverse problem then is to get to restore the map of this initial pressure rise from the detected ultrasound signal, and we can call the map of P0 a basic photoacoustic image. From this physical principle of photoacoustic imaging, there are two main properties that can be used for two different implementations. The first one is the specific sensitivity to optical absorption, and it's mostly used in optical microscopy or photoacoustic microscopy. And the other property is that the excitation light can be scattered. It doesn't have to be either coherent or to be focused, and this property implies that we can increase the imaging depth. So first I'm going to present this photoacoustic microscopy, and which is called ORPAM, so Optical Resolution Photoacoustic Microscopy. So here the light the optical excitation is focused, and the ultrasound generated at the focal spot, the optical focal spot, are captured by a confocal ultrasound detector. And the resolution in this direction is given by the optical focusing, and in the depth it's going to be given by the ultrasound, as we will see in the next slide. The imaging depth is usually lower than 1 millimeter, and it means the optical range is usually in the UV and visible range for this depth. And the excitation and the detection are scanned point by point to reconstruct a 3D image of the sample. When light do not have to be focused and can be scattered, this is photoacoustic tomography, where here the light is shined on the tissue surface, and it scatters in the tissue, and actually what we just need is optical energy to be absorbed. And from this absorption, so you have the ultrasound wave that travels through the ultrasound detectors. They are captured on several detector positions in order to be able to do the image. So here the resolution of the images is the ultrasound resolution, and it's on the order of 100 micrometer. The imaging depth can be as high as 5 centimeters. And for that, the visible and near infrared light is used to penetrate deep into tissue. And usually the excitation is fixed in this configuration, in this implementation. So a few hints on how the image reconstruction is performed. So we mentioned for the photoacoustic microscopy that the resolution is given by the optical focal spot in the lateral direction, so this direction. So in depth, it's given by the ultrasound signal, and if we have two absorbers, for example, at different depth, so the ultrasound signal will look like this. At T0 we have the laser shot, and at this time t equal d divided by the speed of sound, d1, so d1 being the distance of this absorber to the detector, and the other one is arrive at a different time because it's on a different depth. So discrimination is performed in time of arrival, so the depth information is encoded in the travel time of the ultrasound, and the axial resolution is given by the width of the ultrasound pulse, and which corresponds to the speed of sound divided by the bandwidth of the detector. For the photoacoustic tomography, a practical solution is a back projection of the signals into an image grid. So for that, we take the signals that are received, for example, for this detector. We convert the time into space by multiplying by the speed of sound, and the signals are projected on circles or spheres centered on the detector itself and on a radius that corresponds to this distance. So here, for example, if we have one absorber here, the signals will be propagated. Will be projected in this arc here, in this arc, for example, for this detector, for this one in this one, and for this one in this arc. And when we sum, then this spot will appear white, and the rest will be black or grayish. So diffraction, the images are diffraction limited in terms of resolution. So it's the ultrasound diffraction here that applies in all direction, and the resolution in all direction is limited by basically the speed of sound divided by the bandwidth of the detector. And of course, there are more advanced imaging reconstruction process, but I guess for the moment this is the most used, and this is a good way to understand how the reconstruction is performed. So I'm going to give you now a few examples of single wavelength images, and I will start with cells. So individual cells image with label-free. So it's a label-free fibroblast image with a photoacoustic microscope. And the optical absorption at 522 nanometers shows the cytoplasm, mostly because there are mitochondrial chromophores that absorbs at this wavelength. At 250 nanometers, it's the nucleus with the DNA and RNA that absorbs. And with an overlay, we can have an image of the optical absorption, so label-free image of the cells. Another scale for a still optical resolution microscope. This is an image of the brain vasculature image when with the scalp removed but the skull intact, and you can see many different vessel size of the brain of a mouse, and with color coding corresponding to the depth, and you can see that the depth is below 1 millimeter here, and the optical wavelength it's at 532, so in the green here. For the photoacoustic tomography, I'm starting here with a small animal as well. It's a ex vivo zebrafish, 21 day post fecundation, and it's already scattering at this age. And you can recognize the fish with the tail here, the eye here, and absorbers, mostly vessels, blood vessels, the skin, the pigmented skin, and so features that absorbs. And the last example I will show you is a 3D image of the blood vasculature of a mouse. So this is the entire mouse. So you see that the scale bar now is 5 millimeter, and you see here the liver. You see blood vessels. Here it's going to be the heart. So it's the arms that are here and legs below. And you can see the spinal cord here, or the blood vessels of the spinal cord, here the spleen, and many blood vessels, and here the ribs as well. And here you can see that the imaging wavelength is in the near infrared at 800 nanometer. So from these images we can ask ourselves, what are the contrast agents in photoacoustic imaging? And we already saw some endogenous contrast agents, but I'm going to give a bit more here. So in the UV, you have the DNA, RNA that absorbs the light. And then when you go to visible and near infrared, you have the melanin that absorbs quite high. And you have the oxygenated hemoglobin and deoxygenated hemoglobin, which are commonly used. There's also the lipids that start to absorb more in the near infrared, and after that you have the water, and water starts to absorb a lot after 1200 nanometer, and this is why this range between here 650 and 1200 nanometer is defined as the optical window for biological tissue. And of course there are exogenous contrast agents. So I selected 3 categories, and the first one is 3 small molecules like dyes, fluorophore with low quantum yield, which are going to be transferring the absorbed energy mostly into heat, like methylene blue, indocyanin green, cyanin dyes, body-P dyes, and so on. These small molecules, they can be encapsulated in non-absorbing nanocarriers like liposomes or nanospheres. And of course there are absorbing nanoparticles that are directly absorbing, like plasmonic nanoparticles, gold nanosphere, gold nanorods, carbon nanotubes as well are absorbing nanoparticles, and there are also absorbing polymer nanostructures. And there are a vast range of actually exogenous contrast agents, and there are some new coming up every day, so it's just a broad view of the 3 main categories. And from these absorbers, we want to be able to separate the absorbers on the images, and for that some multispectral approach has been developed, and it's based on the Beer-Lambert law that relates the optical absorption coefficient to the sum over the compounds of the molar absorption coefficient times the concentration. So the goal here is to go from this absorption coefficient that is measured by the initial pressure rise, or approximated by the initial pressure rise, to the concentration. So we go from images at multiple wavelengths. So here there are 5 optical wavelengths, and the pixel amplitude is proportional to the P0, and which is also proportional to the optical absorption. And if we know the spectrum from the compound that are expected in the image, so here deoxygenated hemoglobin, and an infrared dye like ICG, we can get images with spectral mixing where the pixel amplitude is actually proportional to the compound concentration. And to give you a few examples, so for photoacoustic microscopy, so it's an image of the human finger, and you can see the macrovasculature of the fingertip. And here the oxygenated and deoxygenated hemoglobin have been separated, and then this oxygen saturation ratio has been computed by the concentration of the oxygenated hemoglobin over the total concentration of hemoglobin. And you can see here a map of the absorption, so this oxygen saturation, where you can differentiate between vessels the oxygen saturation. For the photoacoustic tomography, here it's a cross-section of the imp of a mouse, and the mouse has been under different gas. So full oxygen, you see that the oxygen saturation is quite high. When you have only 20% of oxygen, it's a bit lower, and when the mouse is dead because CO2 has been administered, then the oxygen saturation is much lower. Another example is the human wrist, where you have like here 3 squares that correspond to these 3 images, and here there's a mole on the skin, and you see that melanin has been separated. There are vessels appearing mostly red because of oxygenated hemoglobin, and some mostly blue because of deoxygenated hemoglobin. The one in red are mostly arteries, and the one in blue veins. And this is all, I guess, for endogenous absorbers. And for exogenous absorbers, so if we take, so here in this example, cancerous cells have been mixed with gold nanoparticles, and also they have been under H&E staining. The H&E staining enables to see the absorption of the nucleus at 532 nanometer, and the gold nanorods, they absorb in the near-infrared at 720 nanometer, and having the two images and overlaying them, the different absorbers can be separated in space. For photoacoustic tomography, I show you here an example of something I haven't mentioned yet. It's genetically encoded photoacoustic contrast agent. So cancer cells expressing teronase, which is absorbing, have been implanted in a mouse, and we can separate the tumor, so the cells, from the blood vessels. Another example here, it's ex vivo mouse kidney. So the mouse has been injected 15 minutes before it has been sacrificed with contrast agents, and small molecular dye that is mostly in the renal pelvis is here, and the vessels are shown in white. And gold nanorods that are too large to be excreted by the renal pelvis and the urine, and that stays in the blood vasculature, and we see that the orange color is superimposed to the gray color. Just for if you want to get photoacoustic in your lab, there are commercial implementation for photoacoustic microscopy. It's mostly home-built photoacoustic microscope, but I was able to find one device that can be used in photoacoustic an optical microscope, as you can see here. And for photoacoustic tomography, so here I show you a few examples stored by increasing imaging depth with first a scanning system to image at maximum 5 mm depth for dermatology or shallow depth imaging, but high resolution. Here it's ultrasound imaging scanner that with a photoacoustic module with the light guided in those fiber bundles here and clip on the side of the array. And it's around 20 megahertz, and here it's at lower frequency, and you can image the entire cross section of a mouse to do a mouse or rats imaging. And with that, I thank you for your attention, and I'm ready to answer your questions.